Applications of integration, page 8. A train moves along a straight track with acceleration t over 10 minus 3. The initial velocity of the train is 45. Determine the velocity function v of t. So this time we have the acceleration. They want to know the velocity. Usually they give us velocity and we find the displacement, and we do that with an integral. But now we're going to find the velocity from the acceleration, and we also do that with the integral. Remember that the displacement, velocity, and acceleration are related by derivative, and if we go backwards, we're going to do integral and integral. So the integral of t over 10 is t squared over 20, and the integral of negative 3 is negative 3t. And then they do give us a point. Remember, it's plus c. They do give us a point here, which is that the initial velocity, which is t equals 0, is v equals 45. So we're going to put 0 minus 0 plus c equals 45. So we have immediately discovered that c is 45. Okay. So that's the velocity function. Then it tells us to evaluate v of t equals dt from 0 to 60 and explain what this value represents. Well, the integral of velocity is basically the displacement, right? So we are finding the displacement. The only question is, are we finding the total displacement? Because if there's a direction change between 0 and 60, we need to divide it up into separate integrals. And so let's figure out first where are the equals 0 points for the velocity function. And this is kind of a pain to do by hand because we'll have to use like the quadratic formula or something. And so why don't we just use the calculator for this? They're not going to ask you to do this manually on the test. So we're going to put 1 divided by 20, which is 0.05. It's easier to write that as a decimal. And then we're going to do minus 3t. And then we're going to do 45. And then we're going to graph it. And then we're going to, oops, look at that. It's like going to cross way over here. So we need to adjust our window to maybe like x max of 100. Oh, there we go. So the two intersection points are here and here. Maybe we could do second calc 0 to find those. Second calc 0, left bound, we want to put it over here. Right bound, we're going to put it slightly to the right. Oh, there we go. Kind of in the middle so that we don't catch both. Oops, there was no sign change. It didn't like that. Okay, so let's do the table. That's a little better. Oh, look at that. It does not cross in two places. It only has one 0 point at t equals 30. Okay. So there is oh, but look at that. So the velocity is positive here. It's positive here. So it is always positive. So there is no sign change. We don't need to do it divided into two sections. So let's take the integral of the velocity function, and we're going to get t cubed over 60 minus 3t squared over 2 plus 45t, and we're going to evaluate that from 0 to 60. So if we put 60 in there, we're going to have 60 cubed over 60 minus 3, and then 60 squared would be 3600 divided by 2, and then 45 times 60 minus, and then everything would be, when you plug 0 into that function, you just get 0 out. So let's simplify this. It'd be 60 squared. And then this would be like 1800 divided by 2 times 3. And then 45 by 60. So let's, oops, this would be 2. So let's figure that out here. We'll get in the calculator, and we'll do 60 squared. No, yeah, 60 squared would be 3600. So this would be 3600. This would be 3600. This would be minus 3 times 1800. So 3600 minus 3 times 1800 would be negative 1800. So we'd have negative 1800. And then 45 times 60, I think that would be some multiple of 1800 too. 2700. 2700 minus 1800 is equal to 900. So the answer is 900. And the 900, as there's no sign change in the middle of that, it would be total displacement from in first 60 seconds. Okay. Okay, now we're starting 19D, which is solids of revolution. Consider the curve y equals f of x for the interval a to b. If the shaded area below is revolved around the x-axis through 360 degrees, or 2 pi for you radian fans, a three-dimensional solid will be formed. Such a solid is called a solid of revolution. Draw a sketch of the resulting solid when you revolve f of x about the x-axis. Okay, so we could just do it on top of this here. We go whoop, 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 and you say, hey, wait a second, it's already drawn here. Okay, that's fine too. Use the equation for the volume of the cylinder, V equals pi r squared h, and write volume equations for the three flat discs at the right. So there is a disc here, there's a disc here, and there is a disc here. So the left disc has a radius of f of a, right? F of a is this distance here. So it would be pi times r, which is f of a, squared, times, and remember, this is not f times a squared with the a squared. It is this is like one expression here, f of a. It's the y of the function when a is plugged in for x. Okay. H. And h of the cylinder is like the width of the cylinder. So in this case, we say that our width is small h. Right? So we'll put that. And the middle one is the same thing except for the f has x plugged in. And then finally, the right one is going to be pi times f of b squared times h. Write the decimal integral that sums the volume of an infinite number of infinitely flat disks which stacked together form the solid of revolution. Okay. That's going to be not enough space there, so I'm going to integrate from a to b, and I'm going to put the cylinder equation here. So it's going to be pi times f of x squared h. Now, instead of h, I'm going to put dx. Dx is going to be the infinitely thin height of the disk. Find the volume of a solid formed when the following are revolved through 2 pi around the x-axis. Okay, so now they're actually giving us a real function, and 2x happens to be a line that looks like kind of like that. And so we are going to take from 0 to 3, we're going to rotate it. It's going to make like a really flat cone, right? So we're going to do exactly what we did here. A to b is 0 to 3, and then we're going to have pi, And then we're going to have 2x, which is the function, and we're going to square it, and then we're going to finish off with dx here. And so that's going to be, we can multiply that out. So we're going to have 0 to 3 pi 4x squared dx. And so the integral of 4x squared is going to be 4 times x cubed over 3. And then, of course, we have pi here. And then we can evaluate that from 0 to 3. So that's equal to pi times 4 times 27 divided by 3 minus 0. Okay? So when we evaluate it at 0, it's just 0. So 27 divided by 3 is 9. So that's going to be 36 pi. Wow, what a nice even number. 36 pi. Okay. And we probably could have figured that out too by using the volume of a cone formula. But now we're doing it with integrals. Okay, that's it for page 8. Quick, huh?